Hey everybody, video number 3, solutions and solubility guidelines. There's 3 learning targets. So first, identify the solute and solvent when there's a homogeneous solution. Which is which? Apply the vocabulary. Big one for this video. Use table F to predict solubility of ionic compounds in water. We are going to spend a lot of time on that one. And then also, you'd be able to use the like dissolves like. Not so hard to do. Once you learn what like dissolve like means, you determine if two substances will mix or not. So we're going to blow through some early notes and then get into the meat and potatoes of what this unit or this video is about. So solution implies that there's two substances being mixed. So solutions are mixtures to form one new thing that's the same throughout, hence homogeneous. So it's a homogeneous mixture. Solutions are homogeneous, mixtures. Mixture of what? Well, solute is the stuff that is in the solution that was dissolved. This is the Kool-Aid, if you were making Kool-Aid, the actual sugar and the flavored sugar, okay, and the colored sugar in the packet. The solute is usually in smaller quantity. The solvent is the stuff that's doing the dissolving, so the water. Okay, it's usually in greater amount, usually in a liquid. And I screwed up when I looked at the PowerPoint before I sent this to print shop, and the 3 pieces that go here are on top of each other, or I would have slid you in some more room. So you just have to make notes on how you put this stuff in there. So first is dissolve. There should be 3 lines you have to put in this box. So first, dissolve is the first step. Molecules breaking apart from one another to take the form of the solvent. If you don't have room to write all that, you need to say dissolve is breaking apart, first step, or something to that regard, just breaking molecules apart. Because then dissociate is the next special second step. I say special because not everybody dissociates. Lots of guys dissolve, not everybody dissociates. This is when the compounds break into their atoms or ions, forming specifically an electrolyte. Ionics do this and covalents don't. Okay. And then the last piece is like dissolve like. So this is just our saying. So if you can even remember the saying without writing it, you're fine. This means that the polar solutes dissolve in polar solvents and hence nonpolar. As long as they match up, we're good. And I'm not even going to animate this little box down here. I'm just going to talk you through it real quick. So if I have a polar solvent in yellow like water, and I mix it with a polar solute, will it make a solution? Yes. The answer is yes. Then again, if I have the polar solvent like water and I mix it with a nonpolar solute, no, it will not mix because polar and nonpolar do not mix. Like dissolves like. And then the nonpolar with the polar solute like oil, no. Oil and certain things just don't mix. Oil and water don't mix. One's polar, one's nonpolar. But then if I take a nonpolar solvent like oil and I put a nonpolar solute in there, boom, it will mix. So I think candle dyes have to are special because they have to dissolve in the oil that is the wax. Okay. Quick types of solutions. Alloys are 2 metals put together, usually because I like one of the effects of one of the metals. Improves the overall quality. Aqueous solution, again, is just a solution where water is the solvent. There's some stuff in here about universal solvent, and because, yes, it is called that. There's little kind of tidbits I'd like you to know. Make sure you read it. Do you need to write every word there? Probably not. I'm trusting you at this point to figure out what you need to get through the rest of your unit. Okay. Specifically, colloids, suspensions, and emulsions. I need to make reference to them so you at least know what they are. Colloids appear to be in solution but fail the Tyndall test. I'll tell you what that means in a minute. Colloids look like solutions. They're not. And I'll prove to you why. Suspensions is the actual name for like a mixture of things that you would see, like sand and water, or Italian dressing is a great thing where I can see 2 different things are very visible. We call that technically a suspension because those things are suspended in the liquid that I put them in, but they're not dissolved into that liquid. They haven't taken the phase. And then emulsions, this is a lawyer statement here just to let you know that they do exist. I think mayonnaise is an emulsion, but I'd have to verify that. One of you guys have a Google machine, you can tell me. But I know Kodak was big on emulsions, and that means nothing to you. But again, not true solution, fine dispersion of minute droplets of one liquid in another. Okay, real quick on the Tyndall effect, and we're moving on to table F. So this is when I use a laser. to test to see if it's a solution. So if my solution's in a glass container and I put the laser up to it and I put it through, the laser is going to go right through. It's going to hit the wall. No big deal. It's not one of those super power, superhero lasers. It's just a regular laser like what's in my pointer. And if I can't see it in the liquid, it's a perfect solution. But if the stuff that I put in to make the solution didn't dissolve like it's supposed to, because it's not a true solution, it's a colloid, it'll be big enough particulate wise that the laser coming through will show up, and I'll actually see the laser beam itself in the liquid. If I can see the laser beam in the liquid, that means the stuff didn't dissolve good, and it's technically a colloid and not a true solution. Okay, Tyndall effect. Now you know what that means. Okay, big bad table F. Here we go. There's some little notes on either side. Then we're going to use double replacement reactions to predict solubility. So that's what this video is really the nuts and bolts of what's going on. So everything in this first column in table F, and this is in your reference tables. Notice all of these are soluble because they're in that ions will form soluble compounds column. Almost all of them have no exceptions. So group 1 ions, ammonium, notice they're almost all negative except for ammonium. Okay, so I'm going to teach you to go for the negative ions. Okay, almost all of them are soluble no matter what. Okay, good. And then this particular column is exceptions to soluble. And of course, an exception to soluble then is insoluble. It's soluble except for when it's with this. So if it's soluble except for when it's with this, that means it becomes insoluble. And if you look at these halides, what that means is if I have a halide, like say Cl, and it's combined with Na to make NaCl, notice Na is not on the exceptional list. So NaCl, because it's a chloride, would dissolve. Plus I see Na up top is a group 1 ion, so it dissolves. But if I take something like lead and it's PbCl2, Pb is an exception to the solubility of halides, hence now it is insoluble. See how we read that? This is how we read this. And then the next big box starts with insoluble. So everybody on this side is insoluble. Every one of those guys is generally insoluble. And of course, every one of these guys has an exception. So the exception to insoluble, of course, will be soluble. So I would say, okay, all carbonates are insoluble except for when they're with group 1 metals. So lithium. Lithium carbonate would be soluble because group 1 metals are always soluble, no matter if they're with carbonate or not. See how that works? So the exception to insoluble is soluble. Getting a little bit of a flavor for how to do this. Let's do some examples with just using table F so that we can get on to the nuts and bolts. So filling in this chart, and we need a table to do so. First example is going to be NaCl. I named this by saying sodium chloride. Remember, chlorine becomes ide. We learned this long time ago. Is it soluble or is it not in water? So first I'm going to take that negative species, Cl, and I'm going to find it on here, and I find it's right here. And I see all halides are soluble, except with silver letter mercury. Is Na silver letter mercury? Nope. So this is not an exception to soluble, so it is soluble. Good. Another one. AgCl2. We call this silver chloride. And again, I want to start with that negative species. It makes this go a lot faster. This whole chart is almost all negative except for 2, the group 1 ions and ammonium. So I see Cl. I find Cl was right here. All Cls are soluble except with silver. So silver is on the exceptions list to solubility, and the exception to soluble is insoluble. So these middle 2 columns are insoluble. So this will be insoluble because it's an exception to the soluble rule. Okay. And next one, I see Al. That's a capital A with a little L, PO4. This is aluminum phosphate. I'm going to take that negative species phosphate and locate it on my chart, and I see it's right there. All phosphates are insoluble. Now I look at aluminum and say, okay, is aluminum a group 1 ion? Nope, it's in group 13. And is aluminum the same thing as ammonium, NH4+? Nope, it's not. So it is not an exception to insoluble. So hence it is insoluble. That's simple. Okay, good. So now we need to apply this. And so before we can apply what we just learned, we need to go back and remember all the other stuff we know how to do. So we learned about these double replacement reactions. And if you look at the picture down at the bottom of the screen, this picture I believe is in your practice pages to help you with this when you're doing it by yourself. So I'm just going to go ahead and code this thing up just like that is. And that's what it means by coded. So Mg becomes, sample A, and Br becomes B, and Na becomes C, and CO3 becomes D. See how we just coded those atoms up? And then I'm going to double replace them. So I'm going to take the C and the A and switch them. So now C is going to go first, which is Na, and it's going to be hooked to Br. And I need to make sure that we are very clear on this. You might want to write a side note. Do not bring the subscripts with you unless they are part of a polyatomic ion. Like CO3, the 3 comes because it's CO3. It's on table E. But N2 is not on table E. Br2 is not on table E. So what we end up doing is saying Na's got a +1 charge, Br's got a -1 charge, crisscrossing down 1-to-1, boom, done. It's just a 1-to-1 ratio. Okay, I'll show you a little bit of what that means. This is tough to do without having to be able to write on the board. So you'll have to bear with me on how I can get all this information to you. Anyways, the next molecule that's formed is AD. So I take the Mg and the carbonate CO3. And I'm going to bring the charge this time to show you. Okay, and then CO3 comes over also. The 3 comes because it's part of carbonate. It's part of a polyatomic ion. And on table E, it's got a -2 charge. Well, do my +2 and my -2 charge cancel out? They actually do. So if I were to crisscross these down, I'd go to 2 into 2. And if they're the same, I can reduce to 1 and the 1. Remember when we crisscross, though, we don't bring the charges, we just bring the numbers? Well, it's kind of really tough for me to animate that moving and losing its charge. So that didn't happen. Sorry about it. But it's ends up being a 1-to-1 ratio, so it's just MgCO3. Now that I've done my double replacement, I need to look at both particular products and see if any of them become insoluble. Table F. Okay, so I'm going to find Br. I see Br is under halides, and all halides are soluble except for with Ag, Pb, and Hg. And Na is neither of those. So Br is going to be soluble. Anything with Br, because it's not Ag, Pb, or Hg. Or you could say Na. Na is a group 1 ion, so this whole thing is soluble, period. You can go like that too. I'm okay with that. I just start with the negatives. So underneath there, I'm going to write an S. If you want to circle it, you can. I just did that so it would show up. All you have to do is write the letter. Okay. Next one, MgCO3. I find CO3, it's carbonate. It's listed under insolubles. All carbonates are insoluble except for with group 1 or ammonium. Is Mg in group 1? No, it's in group 2. And is it ammonium? No. So guess what? It is not an exception to insoluble, therefore it's insoluble. I'm going to put an I underneath that. And this is what the lab is. So you're going to have to do all the double replacements for the reactions ahead of time. I'm going to give you what the chemicals are. You're going to do the double replacements ahead of time and predict their solubility. And then you're going to actually do every one of the reactions in a well plate, which is this plastic piece with the little circles in there. You're going to do like 5 drops each in each one and see which ones precipitate and which ones don't, and see if your predictability skills are good. 2 more of these and we'll call it a day. Okay, so next one. Again, I'm going to code it up with the A, B, the C, and the D. And I know that C goes with B and A goes with D to form my double replacement. And if you put the one that says CB on the second and the one that says AB, AD on the first, that's okay. The order of the products does not matter. The order of the ions within the compound does. We always start with the positive and then with the negative. Just so we're clear, I could have coded these positive, negative, and made this positive go with that negative and made this positive go with that negative. That also works if you don't want to memorize this CBD. I just wanted to be able to use this graphical picture, which is in your practice notes, to show you how to do these, so that maybe you can get them done before break is over and you can check your work with my packet. Okay? How'd that sound? So I'm going to take A, C with B first. So C is Ca, B is CO3. I'm going to clicky click. And C goes with CO3. I know Ca is a +2. I know CO3 from just doing this is a -2. So they're a 1-to-1 ratio, and I've built a stable molecule. But remember, the 3 comes with it. Okay? Okay, good. Now, NH4 comes over and Cl comes over. Now, I bring the 4 because it's inside the parentheses. It's in the polyatomic. I do not bring the 2. Just how with chlorine, I don't bring the 2. I just bring these over. I look up ammonium is a +1. Chlorine is a -1. Hence, they crisscross down to 1 and 1. So it's just NH4Cl. I need to have that skill about crisscrossing. So that's a big part of using our old previous knowledge in this particular unit. If you weren't really good at it before, it's time to get on board. So now I'm going to go through and look. Carbonates. All carbonates are insoluble. And no, I didn't animate this, except for with group 1 ions, which is not calcium. Calcium's a +2. It's in group 2. And calcium is not ammonium, so it will be insoluble. I'm going to put an I. And then ammonium. All ammoniums are soluble. So done. Chlorine. All chlorides are soluble except for with silver, lead, and mercury. Ammonium is not silver, lead, or mercury. So this part will be soluble. When I do this reaction, and I can't make F go away right now without making the whole reaction go away. But when I do this reaction, an insoluble product is going to form. It's going to be CaCO3, calcium carbonate. It's like a chalk. And it's going to fall out of solution. And all of a sudden, I'm going to take 2 clear liquids. I'm going to mix them together, and this white powder is going to form. Kind of cool. Kind of cool. Last one, and we are done. A lot of crisscrossing on this one to really help us hammer that home. So again, I'm going to code it up so you see what's up. A, B, C, D goes to C, B, A, D. Okay. I remember I could code these positives, negatives. So let's fill them in. Ca goes with Cl. And I'm going to bring over some charges. And Ca is a +2 and Cl is a -1. So when I crisscross that down and crisscross this down, remember we don't bring the charges. I need 2 Cls for 1 Ca. And if you like to do it while they're still up top and you can see that you needed 2 -1s to combat the 1 +2, there you go. But it's going to be CaCl2. And you have to build the proper molecule. Okay, good. First step. Another molecule. I got NH4 and CO3. In both cases, I need to bring the 4 and the 3 because these are part of the polyatomic ion again, remember. And then I look and say, yo, look, ammonium is a +1, but carbonate is a -2. Uh-oh, Pescadios. So when I bring the 1 down and the 2 down, bring the 1 down and the 2 down, this becomes that now. NH4 with 1 carbonate. That is a properly built molecule. Then I can apply table F. So here it comes. All chlorides are soluble except for with silver, lead, and mercury. Calcium is not silver, lead, or mercury, so I will be soluble, S. Then, last one, carbonates. All carbonates are soluble except for with group 1 or ammonium. And oh, look, I'm with ammonium, so I am soluble. I'm an exception to the insoluble rule. So in this case, I will take 2 liquids, mix them together, and form 2 liquids that are soluble. So I won't see a reaction. I will not see a precipitate in this particular reaction, but notice all the work I had to do to build proper molecules and then check for solubility. And with that, we are donezo. Lots of practice on this particular lecture video, because there's a lot of tasks now we got to be able to do. And of course, mad specific to the first lab we need to do, which is Precip Lab.